All right, guys, we are going to talk about constant motion today. So there's a couple vocab words I just want to kind of get under our belts before we dig into constant motion, which is what we just did our lab over today. So a couple words I want to introduce. Vector. So a vector, if you remember the bad guy from Despicable Me, yes, I'm talking about the same vector. He introduced himself. Remember, he says he has magnitude and direction. So a vector, it consists of both a numerical value with its unit and a direction. So vectors can be positive or negative. I like to think of a vector as I am going 70 miles per hour south on 270. Now the key word here is that south because I'm telling you the direction I'm traveling. So that's a big deal here. I'm going to go ahead and circle that. So circle that direction there. Big deal when it comes to vectors. Examples of vectors would be velocity, acceleration, and displacement. And we're going to dig into each of those this unit. Another one, we're going to have a scalar. So the big thing with scalar is just a numerical value with a unit. So there's no direction associated with scalar. The big one here is time. We don't have a direction associated with time. I can't say 2 seconds left, 2 seconds right. It's just 2 seconds. However, we have some other terms that we use a lot, and the word speed is a big deal here. So speed is a really important scalar for us to know that it's scalar and not vector. Because the speed, if I were to say I'm going 60 miles per hour on 270, I told you the numerical value I'm moving, but I didn't tell you if I was going north or south on 270. So that's why if I just say I'm going 70 miles per hour, it's a speed. Versus if I say I'm going 70 miles per hour south, it's a velocity. Temperature is another one of those. I don't have a direction associated with temperature. And then distance. Distance we're going to dig into a little bit more, so I'm going to go into that in a second. All right. So now we're going to dig into kind of like looking at two different variables that are very similar, but one's the vector version and one's the scalar version. So real quick before we dig into this, I want you to answer the question, what is the difference between a vector and a scalar value in your own words? So now we're going to dig into displacement. Distance versus displacement. Basically, a scalar value versus a vector value. Now, the scalar value does not have a direction associated with it. The vector value does. So let's start with displacement. The word displacement means a change in position. So the idea is if I'm starting at my house, I live in O'Fallon, and I drive to school, Parkway North, and then I drive back home to my house, my total change in position or displacement for the day is 0 because I started and ended at the same place. We're going to typically measure this in meters. And we put a unit with this. Now, you might be given kilometers and you have to change to meters. You might have centimeters and have to change to meters. But in general, we're going to answer this in meters. And the equation we're going to use for this is delta x equals xf minus xi. Now, if you remember from chemistry, this delta, or that little triangle, it really just means change. So change and x in physics means position. So delta x just means my change in position. So we're going to take our final position minus our initial position. On our tests, you're going to be able to use note cards, at least a note card. I'm debating notes right now, like just having open note tests. So make sure you write this down and box in this equation so you're able to come back to it easily. Now distance is the total length traveled. This is also measured in meters. Now the difference between distance and displacement. Again, I live in O'Fallon. I drive to Parkway North every day. So I drive 25, let's just say 25 miles to Parkway North. and 25 miles home. My odometer on my car is continually counting up how far I've traveled, my total length traveled. So every day, my distance traveled is 50 meters because I do 25 to school plus my 25 home, which gives me 50, and we're gonna say miles, even though technically I like meters when we're talking like more detailed examples. So although my displacement is 0 because I started and ended in the same place, my distance continues to grow. I like to think of my distance as like my Fitbit or your Apple Watch or whatever activity tracker you use, to where it's continually counting upwards, while my displacement is just kind of like if I look at like my starting and ending place for the entire day. So I want to go over an example with this. So Danielle has physics first hour, music second, and math third. Fourth hour she has off, so she studies in the library. So we're just going to calculate her displacement and her distance traveled to show that these are two very different types of calculations. So starting off, we're going to start with physics. So she's here first. Then she travels to music. That's for second hour. Then she travels to math for third hour. And then finally, fourth hour, I know we don't have 4 hours right now, but that's okay. She travels to the library. Maybe she has like a study hall or an off block. So if I want to calculate her displacement, I'm going to use the equation we have. And anytime in physics we're using equations or doing calculations, we're going to write that base equation. It's kind of saying, hey, this is where I know I need to start. So I'm going to say delta x, my change in position, equals xf minus xi. My position final, so the spot Danielle ends up at is the library, which has a position of 0. So for my final position, I'm going to write 0 minus her initial position. Now initially, she starts at the physics classroom, which was located at 5 meters. So I'm going to say 5. So if I do 0 minus 5, she has a total displacement or change in position of -5 meters. The negative is allowed because she's going to move backwards 5 meters. And we can look at this as she starts here, and when it's all said and done, she's going to end here. The difference between these is -5. So I want to calculate her distance traveled. Now the distance traveled, I want you to answer the question, what is different between distance and displacement? So answer that in the question right now. So distance is always going to keep adding up. It's going to keep growing and growing and growing, kind of like your Fitbit or the odometer on your car. So I'm going to start and look at how far she travels from first hour to second hour. Now she's going from 5 to 14, so that gives me a difference of 9. And there's no technical equation here, so you don't really have to write your equation. So 9 meters plus, now from second hour to third hour, she's going to travel from 14 to 8, which is a difference of 6. So plus 6 meters, because that number is just going to keep growing because it's a distance. Then she's going to go from 8 to 0. So we're going to have plus 4 meters. What's the distance Danielle traveled? And by the way, I definitely wrote this wrong. So I paused there for a question, but I didn't write the right number. Let's write 8 meters there like it should be. All right, so what's the distance Danielle traveled this time when I actually put the right numbers in? You should have gotten or selected 23 meters. All right, let's dig into velocity versus speed now. Now we're going to dig into velocity versus the average velocity versus speed. So kind of 3 things here. So when I'm talking about velocity, velocity is the displacement per unit of time. So this is measured typically in meters per second. So that's going to be our unit that we're going to be looking for. And it does not have to be the starting and ending point. So I'll talk about that when we're doing graphs. So what this equation means is my velocity is going to be equal to, a little more room there, my change in position, delta x, over my change in time. Now reminder, delta x is xf minus xi. So change in time would be tf minus ti. Now we can calculate this by looking at a graph, and this should look very, very similar to another equation you've seen in math class. I'll write it in a different color real quick. Let's say y2 minus y1 over x2 minus x1. Our slope equation. My math teacher in high school called this yum-yums on the picnic table because she said that this bottom part with the fraction sign looked like a picnic table, and you put your y's on top because they were your yum-yums. Now speed. Speed's kind of similar to, it's a scalar value, so it can't be negative. But speed is just the absolute value of velocity. So let's say we have an example where we get, somehow our answer is, our velocity was -2 meters per second. Our speed would be equal to +2 meters per second. This is kind of the idea that I don't know which direction I'm traveling. So I can say I'm driving 60 miles per hour on the highway, and that's my speed. But if I said 60 miles per hour south or negative, it would make it a velocity. Now, average velocity is kind of the same thing as the normal velocity, except we have to use specific time frames. So we're going to do an example of that to kind of help you out understanding what I mean there. So let's start with calculating the velocity of the object from 0 to 5 seconds. So in our lab, we came up with this with position versus time graphs. This graph is a little more complicated than the one we came up with. We came up with just a straight lined one, but in general, it's the same type of graph. We can see that it's moving in the positive direction at a constant rate, and then whatever this graph represents, this object stops because the slope turns to 0. So we're going to start by calculating the velocity of the object from 0 to 5 seconds. So we can use our equation delta x over delta t, which is really xf minus xi over tf minus ti. Now we can pick any 2 points along this line. Now, personally, I'm going to pick my starting and ending points because I like to use 0, 0 to help me out. So my final position is 25 because that's where this object ends up at. So 25 minus my initial position, which was 0, divided by my final time, 5 minus 0. This gives me 25 over 5. What's my velocity of my object? You should have said 5 meters per second. Awesome. Now for average velocity, it's a little bit different because this is asking me for the average velocity from 0 to 10 seconds. So they're asking me what's the average. Now technically I could find the slope at every single one of these points and then divide it by my time, or the amount of times I have it. Now or add them up and find the average. I'm not going to do that. Instead, I'm going to add a line to my graph as if I have another line that goes, I went straight from 0 to 10 seconds. I didn't or my position went straight, like a constant, right? I didn't actually stop like the graph suggests. So I'm going to find the slope of this line. So velocity average equals my change in position over my change in time. But I have to use the starting and ending points now, or points that fall on this line. I always use the starting and ending points. So we're going to have xf minus xi over tf minus ti. This gives me 25 minus 0 over 10 minus 0. 25 divided by 10. What does that give me my average velocity to be? 2.5 meters per second. Now this is why it's really important to pay attention to what you're asking, because first off, our times were different that it was specifying, but also if I read that question wrong, could have got a completely different number. All right, one more topic I want to talk about with these sets of notes, and then you should have everything you need to be successful in completing your Mastering Physics. So we're going to talk about motion equations a little bit. This graph should look kind of familiar. You have one with a cat and a dog at the end of your lab, but pretty similar. And we're going to talk about how this graph can be useful for doing calculations. So we've all seen this math equation, y equals mx plus b. M is my slope, and b is my y-intercept. Now, a lot of times in physics, all we do to come up with our equations is take a math equation and relate it to a graph. So in this situation, we're going to relate our math equation to this position versus time graph. Now, y, the variable on my y-axis is x, but specifically I'm going to say it's x final, because my x initial is represented by my y-intercept. So x final equals, and we should have come up with this in our lab, velocity, which is what our slope represents of an xt graph, times our time, the variable that's on my x-axis, plus, instead of b, I'm going to call this position the initial position. And you'll notice that each of these kind of have a pair in the equation. We will do this a lot in this class, so don't worry if you're still kind of lost on this. This is another one of those really good, really important equations for physics. So I would box this in, make sure you have it written down somewhere so you are fully aware of this equation. Now we can take this equation and relate it to each of our people here, Will and Andy. Now, if I want to write a motion equation for them, I'm going to leave xf the same. So if I'm writing a motion equation for Andy, I say xf equals, and then I need to plug in my velocity. However, I don't know my velocity for Andy, so I have to find that real quick. I can pick any 2 points along the line. I'm going to choose ones that kind of go through these crosshairs just to make my life easier. So I'm going to choose this point 4,600, and I'm going to choose 0, 0. Now my velocity is my change in position over my change in time, or just my slope of the line really, which gives me 600 divided by 40. So Andy's velocity is 15 meters per second. So instead of v in my motion equation, I can write 15 meters per second. Now, just like when we're doing a math equation, how we leave y and x in the equation, we're going to do the same thing here. So we're going to leave the one that represents y in our equation, and we're going to leave the one that represents x in our equation. So now we're just going to say 15 meters per second times t plus 0 meters, because for this situation, my y-intercept was 0 meters. We're going to repeat the same process for Will. So I need to see that graph still. xf, because we leave that value in there, equals, and we need to figure out Will's slope. Now Will here, he's got a point that goes through 10, 800, and let's just get a little crazy and go through another point that's not 0, 0. So we need to find the slope of this line. Velocity equals my change in position over my change in time, which gives me x final, which is 200, minus x initial, which was 800 up here, divided by my time final, which was 40, minus my time initial, which was 10. This gives me a velocity of negative 600 divided by, what does that give me, 10? That doesn't give me the right number. What did I do earlier? 40, 10, oh, let's fix that real quick. I wrote a 30 here. It's supposed to be 10. I did the math in my head of the difference of 30 already. Divided by 30, this gives me a velocity of negative 20 meters per second. So instead of instead of writing v, I can write negative 20 meters per second, and I'm going to leave t in there, just like in math class we leave our x and our y's in there. Now for Will, we get a positive intercept because Will actually starts the graph up here. So we get a plus 1,000 meters. 2 questions left, bear with me, you're doing great. So what time will Will and Andy meet? Now, just like in math class, I can kind of eyeball this on the graph. I can look at my graph and go, okay, Will and Andy are going to meet, like, I don't know, somewhere between 25 and 30. And I can also see the location they meet. It's going to be somewhere after 400. But we can actually use math to figure out what this exact time and location is. To do this, we're just going to set our 2 equations equal to each other, because the time they pass is when the final positions are equal. So I can say 15t is equal to negative 20t plus 1,000. You'll notice I lost my units there, and that's completely fine. So now I want to get t by itself. So I'm going to add my 20t the other side, which gives us 35t equals 1,000. To get t by itself, I want to divide by 35, which gives me a time of what? We're looking for 28.57 seconds. And if you're off on your rounding, that's okay. That's the time they're going to cross with each other. Now, if we compare it to our graph, we said it's going to be somewhere between 25 and 30 seconds. So that actually works out pretty well. And then finally, if we want to figure out the position they pass each other, all we have to do is take this time and plug it back into either one of our equations up here. I'm going to plug it into both just to show you that we get the same answer. So for Andy, his equation was xf equals 15 times our time, 28.57. And that gives me a position of 428.57 meters. If I plug this number in for Will, do you think I will get the same or different answer? All right, Will, we're going to get negative 20 times 28.57 plus 1,000. So I'm going to start by doing my negative 20 first. So I get xf equals negative 571.4 plus 1,000 equals 428.57. All right, this is really what we need to know about constant motion. All of these topics are going to be covered on your Mastering Physics assignment that is going to be due on Monday. Please let me know in class if you have any questions over these topics.